Here's an iterative process. Let f of x equal to the function 2x to the third plus 2, all divided by 3x squared. Find f of 1. Okay, so here instead of having like f of g of x or f of g of 1, we keep recycling the same function. So the input goes into f, and that output goes back into f, and that output goes back into f. So this repetitive process is an iterative process. Iteration has something to do with repetition. And so I'm not sure the precise Noah Webster definition, but you can look that up. But anyway, it's an iterative process, and this one has a purpose, and I'll give it away. This is going to get us an estimate of the cube root of 2. All right. Now, other than seeing 2's and cubes up there, it's probably not terribly obvious why we should get the cube root of 2. I would have to explain that with some calculus, so something called Newton's method. Can't do that in this course, so let's just have fun with it and see what happens. So this ends up just being arithmetic, actually. So first of all, I'm going to look at f at 1. And f at 1 is, we can do that in our head. So put 1 in, I'm going to get 2 plus 2, it's 4 over 3. I get 4 thirds, which is 1.333333. All the 3's. So now I'm going to punch in 4 divided by 3. And on my graphing calculator, I hit store x, STO, arrow x. And so now my calculator thinks that x equals to 1.3333333333. All right, 4 thirds. So if you have a graphing calculator, you can learn how to do this if it's interesting to you. Actually, you could use the memory and recall buttons on a scientific calculator to do the same thing. But once I have that number, I can now plug that in to my function pretty easily. So f of 1 is the same as f of 4 thirds. So I'm going to actually just type this in. I have to put parentheses around my numerator. But I'll get, parentheses 2x raised to the third plus 2, close parentheses, divided by parentheses 3x squared, close parentheses. I get, 1.263, and then a very long string of 8's, and it rounds it off to 9 at the end. But it's an infinite string of 8's, I'm sure. All right, so that was that result. So f of 1, which is what we were looking for, f of 1, ends up being f of this function, of this value, 1.263 and a long string of 8's. Now, it would be better to use all the decimals you have on your calculator if you want precise results. So if you round this off, you're going to create errors, and you won't get a very good answer. So in my case, I can just take the answer and hit store x, and then repeat my calculation, and this ends up being 1.25993349345. That's what I'm showing on my screen. All right, now the cube root of 2, if we punch that out, so I'm taking 2 raised to the 1/3 power. I get 1.259921049989, which is pretty close to this one, isn't it? Pretty close. In fact, I'm pretty confident if you did this one more time, went to a 4th iteration, that you probably would get this number, or it's going to be accurate down to the last 1 or 2 places. So I'm just doing that from experience. I know that's what normally happens. So, so here's a repetitive process where the output became the input, and it just kept being recycled. Use the same function to recycle itself, and And what happens is that it converges to a number. And this converging to a number, the number is called the limit point of the function. And so anyway, it's neat. There are processes out there. Again, I like to refer to the high-tech world sometimes. There are processes in high-tech engineering or science applications where solutions are found by this type of iterative, repetitive process. Now, it usually looks a lot more complicated than what I've got. They may be using matrices or something else, but the idea is similar, where you take an output and recycle it back in as an input, and that iterative process will converge to the solution you're looking for. And all right, so I'm going to leave it at that. If I got time, I'll record a card trick on video to show you where you see this iterative process is the magic of the card trick. So anyway, let's leave it at that.